Okay, recording world is on. So now it's like you on YouTube. You can hear your voice right now. You want to say something, don't you? Say something to YouTube.
Hello.
Wow. Okay. Kayla. Wow. Aggressive. She steps out there, and now the voice is on the internet for all the world to hear. All right. So we got over our first day fears. Here we go. Fundamentals, college algebra, real numbers. We start here. Real numbers. Natural numbers. Natural numbers are numbers like 1, 2, 3, so on and so forth. We use an N with a double line through the back in order to symbolize natural numbers. Anybody know why we call them natural numbers? They're your counting numbers. So when I taught Tenley how to count, she starts with 1. Okay, that's just what comes natural to us. So whole numbers include what other number? 0. True or false? All whole numbers are natural numbers. False. True or false? All natural numbers are whole numbers. True. Integers. What do integers include? Negative numbers. Thank you. Here's a Z. No, I didn't make it up. I know some people think I invented mathematics. Not true. Just writing you what the textbooks have. Okay. Rational numbers. What's the root word of rational? Starts with an R. Rhymes with ratio. Ratio. Good. So a ratio is like a fraction. All right. So like 4/5 is a rational number, but it's not an integer or whole number or natural number. Give me another number that's a rational number. Come on. I wrote 1. You can do another. 2/3. Great. Cool. So 0.66 repeating is a rational number. So a decimal can be a rational number. Anything that can be expressed as a fraction is a rational number. Okay? So we've got that. Is number 0 a rational number? Yeah, sure it is. It's sitting right inside the rational numbers. 0 over 2 is a rational number. 0 over 8 is a rational number. Okay? Is number -5 a rational number? Sure, -5 over 1, -10 over 2, -25 over 5. Any of these numbers you could write as a fraction. 3 can be written as 3 over 1, or 9 over 3, or 27 over 9, or 30 over 10, right? So, it can be expressed as a fraction. Okay? What is a number that can't be expressed as a fraction? Pi. Thank you. Give me another one. Square root of 9, that's 3, so that doesn't work. Square root of 2, that was a good one. Natural log of 8, it's a real icky number. A lot of logarithms are, that's the way they are. Cosine of 60 degrees, that's actually square root of 3 over 2. So those are numbers that are irrational. We use the letter Q for rational. I don't know what they use for irrational. I'll have to look it up. And then those all sit within the set of real numbers. Irrational numbers are interesting because there was actually time in the world where people refused to talk about irrational numbers. They didn't think that the world would be designed or that the universe would be designed in a way that would incorporate something that was not expressed in a rational way. And so there were a group of people that didn't believe that the square root of 2 actually existed. Like it does terminate at some point. And this was actually a focal part of the religious belief. In fact, if you talked about the square root of 2, like, I believe in the square root of 2, they burn you at the stake. They're like, you're done! You think that there's irrational things in this world, you're done. Boom, light you on fire. Done. So we've come a long way as society. All right. I know we all have maybe religious differences and political differences. We need to set them aside. If anybody here have a problem with square root of 2, is everybody okay with it? Okay. All right. See how far we've come? Thank goodness. All right. True or false? All irrational numbers are real numbers. True. True or false? All whole numbers are rational. True. True or false? All rational numbers are integers. False. Give me an example of a rational number that's not an integer. 4/5. Okay. True or false? Some rational numbers are natural numbers. True. True or false? Some irrational numbers are integers. False. Okay? So you can see that these are subsets of one another. The only thing that irrational numbers are a part of is real numbers as a whole. Otherwise, these are subsets of one another. Now, that said, if there are real numbers, then there are also what? Imaginary numbers. They're part of the complex set, and the complex set includes numbers like the square root of -1, which is I, or say 2 plus I roots of 3. Now, those are examples of complex numbers, and we'll deal with those later on. They're very important. They change the world. The world's a better place because of them. You may not believe me right now, but trust me, it is true. And that's that. So that's our introduction to sets and subsets, and so that we can start to work with this interval piece and whatnot there. So it says write an inequality for the following and graph each set. So inequality that describes, this is interval notation. We have brackets, we have parentheses. If I want to describe the inequality, this is all numbers between 3 and 5 that could be equal to 3 and 5 as well, right? So I'll put x between them, between 3 and 5, and x is greater than or equal to 3, but it's less than or equal to 5. So that's my inequality that represents that interval, and then I will graph the set. 3 and 5, open or close circles, closed, and are the arrows going to come together or go apart? They're going to come together because this includes all numbers between 3 and 5, so it's a union. They're together. Okay, we'll try C. Sometimes I like to make the graph first so then I can describe the inequality. I will plot 5, open or close circle, open, and the arrow goes to the left or right? Goes to the left because negative infinity is over there. I don't like to write negative infinity down somewhere. It's like, it's not on the number line, is it? And if you were to put negative infinity right there, I'd be like, well, how about that? And that's a little bit further away, isn't it? So putting infinity on a number line is kind of, I don't know, this gives me the heebie-jeebies. So anyway, let's describe this. This is all numbers that are what? All numbers less than 5. No equal sign underneath because we have open circle and we have parentheses on the 5. You do B and D on your own. Go. All right, here we go. You got it. Graph, we've got -2, we've got 0, should be closed circle, open circle. And for the inequality, x is between -2 and 0. It's less than or equal to 0, but it's greater than -2. Questions on that? Good. -23, I plot -23. I do a closed circle, arrow goes that way. X is greater than or equal to -23. Any questions on that? Technically, you could write it like this: x is greater than or equal to -23, or -23 is less than or equal to x. They would never, ever, ever write it like that in a book. So I would really encourage you, please try to write it with the x first. Yes. Do not include the infinity, and that's not dumb. It happens all the time. Don't include the infinity. Don't include it. Okay. Infinity is only included in the interval notation. Can infinity ever have a bracket on it? No, because you cannot point to infinity on the number line. There's always a spot further. There's always a spot further. I was so mesmerized by this that I wrote a song I'll perform for my calculus class this year. It's called Ode to Infinity. Maybe you heard it last year. Coffee House? Rika did it? Make millions on that. Okay. All right, we're going to switch it up. Now we're giving the inequality. Write an interval for the following and graph the set. We'll just do a couple of these. We'll get rid of that one. So we'll do B together, and then you do A and C on your own. So the interval, again, I always like to start with the graph. Getting a visual is sometimes the most helpful piece. So we got 2, open or close circle. Open, arrow goes to the right. And so it looks like 2 is going to be the number on the left. And then I will put infinity to the right. And I do not include 2, and I can't include infinity. It's unbounded. You go ahead and do A and C. Go. What do you think? Good. Any questions on example 2? Once, twice. So this will be the first question on your test. I expect that these will be easy points. It doesn't mean that you'll necessarily get it. You might make a small mistake. I continue to make small mistakes all the time. That said, if you have no idea how to do this type of problem, we really need to sit down and work together, okay? So come in and see me and get some help. All right, example 3. Find the indicated set if A is the interval -2 to 6, B 0 to infinity, C to -1. Provide a graph as well. We're trying to find A union B. Union means that we include, it's both together. I'm sorry. So let me express this. Okay. Union. Combined set. Whereas this symbol is what we refer to as the intersection. So that's the overlap. So if we want to look at A union B, that means all the elements of A union with all the elements of B. So the question is the number 0 in A union B? Yes. Is the number -3 in A union B? Is the number -3 part of this? Is it part of this? So because it's not part of either of them, it's not part of the union as a whole. The number 25, A union B, is 25 in this set, but is it in this set? So it is part of A union B, okay? So union means it just has to be part of one of them, okay? Intersect, it has to be part of both, okay? That's the difference. I like to show this by making a graph. So A union B, we'll draw A, and we'll draw B on the same number line. A is from -2, and then I have 0, I have 6, and I have infinity over there. I will now draw the graph to represent both sets. A is from -2 to +6. B is from 0 to infinity. Okay? Oh, yes, thank you. So the fact is, if we're doing A union B, it doesn't have to be part of both of them, but just one. So is the number -3 part of either of them? No. How about -1? How about numbers here? How about numbers here? So it looks like everything after -2. Do we include -2? No. So the indicated set would be from -2 to infinity. That would be the graph that shows that. You try B on your own. Go ahead. Out of here, 1 o'clock today, 1 o'clock. So what you got? So it just has to be part of one or the other. Is the number 10 part of either A or C? No, so it's not included. But it just has to be part of 1. Okay? Okay, now let's look at intersect. A intersect B. So I'll draw the same graph basically, but I just interpret it differently. So -2, 0, and 6. And A is going to be from -2 to +6. And then B is going to be from 0 to infinity. Okay? And intersect means the overlap. It must be part of both sets and not just one set. So am I part of both here? How about here? How about here? Yep. How about here? No. So this is the only section that I'm looking at that really matters and counts for my indicated set now. I'm going to include from 0 to 6. And so again, I think making a graph is probably the best way. You can just look at the numbers, but it does say provide a graph, and it would just be easier to graph that first. Okay. So for people who struggled on our entrance worksheet with the very first problem that talked about writing an inequality, I always think it's easier to make the graph first. You go ahead and do D, E, and F. When you get an answer, be brave and just come put it up on the board. We'll applaud you whether it's right or wrong. Doesn't really matter. We just want people to put an answer up there. You don't have to put the graph. You just need to put the indicated set. Okay. Well, let me press pause so then we can, so that way other reason might like do this out. Any mistakes? So, let's see. B union C. So we're doing unions. We're combining the two. So B union with C. So this one starts back at -6, and it goes all the way over to infinity. So it looks like that one's good. This was just the intersection or the overlap between the two. So looks like this one has some negative numbers. This one doesn't have any negative numbers. It only has positive. And these positives only go to 1, so 0, 1 looks like it's going to be correct. Right? I didn't make a mistake there, did I? And the last one, 0, 1. Let's actually draw that out. So we've got all of our numbers here. We've got -6, we've got -2, we've got 0, we've got 1, and then something over there, 6. And then we go on forever. So we've got -2, open circle to 6. That's 1. And we've got 0, closed circle, all the way over here. And then we've got that last one, -6. And that's going to bring us right over here to 1. So you're looking to overlap between all three, which is right in here, 0. Very good? Piece of cake? Upside down. Good. All right, we're going to do a little bit on exponents, and then you'll get your assignment. It'll be time to work. All right, so we move on that. We move into exponents. Why? So we have more time tomorrow to deal with harder exponential problems, because those will definitely be more difficult. Anything in 0 power is 1. Why? What do you do with exponents when you're dividing? You subtract them, and so you get x to the 0. And we also know that when you take something divided by itself, you get 1. So I'll put those two together, and anything in 0 power is 1. It's just always a reason in math. It's not like, well, that's just what they said. You know, no. It all works back to something. There's reasons behind it. Okay, if we multiply, what do we do to the exponents? And if you divide, we already said you. And what if I have two things separated by multiplication taken to a power? Can I apply that power to both of them? Yes, I can. A to the m times b to the m. What if it was a plus b to the m? Can I distribute the exponent to both terms there? No. So for example, let's say you had the quantity x minus 3 squared. Some of you would say that's x squared minus 9. Well, no, not at all. Why? You have to take x minus 3 times x minus 3, and you end up with a middle term. So you can't distribute exponents across, addition and subtraction. Totally illegal. Send you over to Nelson, cut your finger off, okay? All right. going on here? What? Oh, it's beeping at me. Okay, all the lights blinked up there for a little bit. Okay, all right, all right. Sometimes when I do too confusing math, the smartboard becomes a dumb board, and it can't keep up. All right, a over b to the nth. Same thing here. We could distribute a to the nth over b to the nth. What if we have a negative exponent for number 6? Flip them, so it becomes b to the nth over a to the nth. Again, 7. What are you going to do? B to the m over a to the n. How about if you have a radical of two things multiplied? Can you separate that? What? Very good. Two square roots that are divided, you could write them as one square root. A over b. And what if we have an index? Like the index here is 2. This is a square root. We don't write the 2, but it is a square root, so index is 2. What if we have an index different than 2? How do we write this as a fractional exponent? A to the what? Does the m go on top or bottom? M goes on top, m stays close to the a, and then the n just swings down to the bottom. So a fractional exponent. Okay. So those are just some, abstract rules. Let's apply them now and do some problems quickly. Some basic exponent. We'll just do example 1, a through L, and then we'll give you your assignment. Value H number 4 to the third is 64. Negative 2 to the fifth. Do you apply the 5 to the negative or just the 2? Just the 2. This is negative 2 times 2 times 2 times 2 times 2. That's what that is. It's not the negative 5 times. It's just the 2 5 times, then the negative. This ends up to be what? Negative 32. Whereas the C, do I apply the negative each time? Yeah, so negative 3 times negative 3 times negative 3. So you get negative 27. Okay? So be careful with your negatives, especially when you punch them into your calculator, that you're smart about that. Okay? Put your parentheses if you want to include the negative. If you don't, then leave it out front. 11 to the 0. 1. And now you know why. Square root of 144. 12. Should I put negative 12? Negative 12 times negative 12 is 144. If it says x squared is 144, how many solutions do you have? 2. So you'd list both positive and negative. But that's not what this is asking. Anytime you're asked to find the square root of a number, you just list what we call the principal root, which is the positive. Which in this case is positive 12. If you take square root of a negative, come up with an imaginary number, right? So we'll let that be right now because we're just talking about real numbers right now. So can you take the cubed root of a negative? Because a negative times a negative times a negative is a negative. So, sorry. And that's good. Thank you for answering. So negative times a negative is a positive, but negative times a negative times a negative is a negative. So what do you cube to get 125? 5, and so the negative would be negative 5. Negative 5 times negative 5 is positive 25, times another negative 5 would be negative 125. What do you multiply by itself 4 times to get 81? 3. 2 to the third times 3 to the negative 2. Ooh boy. Write it so it doesn't have a negative. How would I write that so it doesn't have a negative exponent? 1 over 3 squared. Thank you. Now that we don't have a negative, now we can actually work the problem out. What's 2 to the third? 8 over 9. 8 ninths. 1 over 3 cubed times 6 squared. 1/3 times 1/3 times 1/3. 1/27. 6 squared. Can you simplify 36 over 27? 4/3. Top and bottom divisible by 9. Square root of 5 times square root of 45. Can you multiply those two together? Yes. What's 5 times 45? 225. Very good. Now, can we simplify the square root of 225? What do you get? 15. Was multiplying 5 times 45 in your head difficult for some people? Yeah, should be. Yeah, we don't do it very often. Okay. I guess maybe 5 times 40 is 200. 5 times 5 is 25. Add them together, we get 225. Fine. Let me show you how to do it without actually multiplying them together. Because who wants to do 3 times 48? It is 196, but, what if you really aren't thinking that? Well, it's not that bad. What's 3 times 50? Oh, I bet 144, excuse me. So 150, there I go. And then it's just 2 less, so times 3 is 6, subtracting, you get 144. But, look, let's just separate them. What multiplies a 48? Let's do 16 and 3. Now I don't have to actually multiply them together. What's square root of 3 times square root of 3? Square root of 9, which is 3. Square root of 16? 4 gives you 12. See, that way I could use my properties as square roots to separate them in order to, figure it out a little bit more quickly. That way I didn't have to work with such a big number. So I get 12. Okay, last example. 2 to the negative 3 over 4 to the negative 2. What do I do? Flip it. Yep, so I got 4 to the 2 over 2 to the third. 4 squared is 16 over 8, which is 2. Very good. That's it. Pretty easy, right? You do it. Basic ones. Tomorrow, we look at more difficult ones, okay? Tougher stuff. So if you flip to the front of your notes, very front, there's a space right up front there where you could start writing down your assignments on top. And your assignment is going to be, let's see if I can find this. Okay, this was my old one that I wanted to go away. There we go. Section 1.1, page 12, numbers 29 through 40. Yes, I'll give you a book right after this. And then section 1.2, page 22, numbers 8, 9, 12, 19 through 22. And I hate to break this to you, but the homework really is pretty consistent all year long. We don't end up with too many times where it really slows down. I got a lot of material to get through in this class and not a lot of time, so we really do push. And when I write down problems, I don't try to write ones where it's like, oh, you're going to do the same thing over and over and over again. I do try to pick ones that it's like they're going to need this in order to help them out. Everybody got it? Okay, so I'm going to take my recorder. I press stop.